All right, so the next thing that we're going to talk about now in 4.2, we're going to talk about relative extrema and graphing polynomials. And really, this is just more information relating to the idea of increasing and decreasing functions and related to the idea of concavity. So we're really just building on what we talked about in 4.2. So let's get into it, right? So a function f has a relative maximum at x naught if there is an open interval containing x naught on which f of x naught is the largest value. And similarly, f has a relative minimum at x naught if there's an open interval containing x naught on which f of x naught is the smallest value. Relative maxima and minima are just called relative extrema in general. So a relative extremum is either a relative maximum or a relative minimum. Okay. Here's a picture. So imagine that you had this really kind of messy function, right? You have all these peaks and valleys. The tallest peak would be the absolute maximum of that function, and the lowest valley would be the absolute minimum of that function. But the other peaks and valleys are still relative minima and maxima, or maxima and minima, I guess, respectively, right? So like this point right here, for example, even though it's not absolutely the smallest point on the graph, it is the smallest point on some neighborhood of the graph, right? So it is a relative minimum. And just like this one is a relative maximum, and this is a relative minimum, and this is a relative maximum, right? This is a relative maximum. This is a relative minimum. It also happens to be the absolute minimum. So we'll come back to the concept of absolute extrema in a couple of sections. For now, we're just going to focus on relative extrema, right? So basically, you can think of it like the peaks and valleys of a graph. So a couple definitions, okay? We call x a stationary point of f if f prime of x equals 0. You didn't know this, but in 4.1 we practiced finding stationary points a whole bunch, right? Every time we took the first derivative and then set it equal to 0 and then tried to solve for x, what we were doing was finding stationary points. Okay, so now we have a name for that. Okay, so that's the first definition. Second definition, a point in the domain of f that is either a stationary point or a point where f is not differentiable is called a critical point, or a critical value. In some texts they call them critical values, and I might slip and call it critical values. But a critical point is a place where either the function is not differentiable or where it has a stationary point. Okay? So keeping that definition in mind now, we have the following result, okay? If f has a relative extremum at x naught, then x naught is a critical point of f. Okay? And here's a picture of what it is that we're trying to say. So if you have a relative extremum, like a relative max here, or a relative min there, whatever, then it must be the case that either the derivative is equal to 0, right? The slope of the tangent line is equal to 0 at that point. Or it could be the case that you have like a cusp, like this or that, in which case the function is not differentiable. Okay? So if f has a relative extremum at x naught, then that means x naught must be a critical point. In other words, it's either a stationary point or it's a place where the function is not differentiable. The logic does not flow in the other direction. So just because a point is a critical point doesn't necessarily mean that it's a relative extremum. And we'll talk about this in a little bit more detail in a second. Okay? But the logic does flow in the direction that I've written it here, right? So if you have a relative extremum, then it is a critical point. Okay? So let's practice first of all just finding the critical points of some functions. So let's find the critical points for f of x equals x cubed minus 3x plus 1. Okay, again, critical points. These are going to be places where either this function is not differentiable, or where it has stationary points. Okay. So let's see. Let's in order to tell if and where the function is not differentiable, it helps to take the derivative, right? So I'm going to go ahead and differentiate, and I get 3x squared minus 3. This function, the derivative function, it's defined for every real number x, which means that the original function f is differentiable everywhere. Okay, so it doesn't have any places where it fails to be differentiable. Therefore, the only critical points, the only possible critical points for this example must be stationary points. So we go about finding stationary points by setting the derivative equal to 0 and then solving for x, right? So we're going to get 3 times x squared minus 1. That means that 3 times x plus 1 times x minus 1 is equal to 0, which means x is negative 1 or x is positive 1. Okay, and that's that, right? So those are the critical points of that first example. Here's another example. Let's do this for f of x equals 3x to the 5/3 minus 15x to the 2/3. Let's find the critical points. So again, I'm going to start off by taking the derivative. 3 times 5/3 would just be 5, right? So this is 5x to the 5/3 minus 1 would be 2/3. Okay, minus 15 times 2/3. The 3 will cancel 3 and leave a 5. 5 times 2 would be 10. So it's going to be 10x to the 2/3 minus 1. 2/3 minus 1. That's 2/3 minus 3/3. That's negative 1/3. Okay. Okay, I'm going to simplify this a little bit by factoring out. Remember, you can always factor out an x with whatever the smallest exponent is. So in this case, I can factor out an x to the negative 1/3. Oh, and I can take out a 5 too. So I might as well do that while I'm at it. I'm going to take out a 5x to the negative 1/3. And now what am I going to be left with? Well, I subtract, right? If I factor out that, I would subtract 2/3 minus negative 1/3 is 2/3 plus 1/3. That's 3/3. That's just x. Okay, and then here, if I divide, right, 10 divided by 5 is 2, so I'm going to be left with 2. Just 2. So there you go. And then I can simplify that a little further and say this is x minus 2 over oh, well, actually, I suppose the 5 would remain up here, right? It'd be 5 times x minus 2 over x to the positive 1/3. Okay, very good. So now, this is important because this function does have some, it does have a point where it's not differentiable. And that's going to happen whenever x equals 0, okay? Because where x equals 0, the derivative function is undefined. And so the derivative function, since the derivative function is not defined at x equals 0, that means the original function is not differentiable at x equals 0, which means that 0 is a critical point. Okay? So maybe we could say something like this. F is not differentiable at x equals 0. So x equals 0 is a critical point. I'm just going to abbreviate that CP. Okay, But then there are also stationary points, right? Because if we let f prime of x equals 0, so this is finding the stationary points now. We would let f prime of x equal 0, so in other words, we would have 5 times x minus 2 over x to the 1/3 equals 0. So in other words, 5 times x minus 2 would be 0. That would mean x is 2. Okay, so x equals 2 is a stationary point. So my critical points, right, critical points are going to be 0 and 2. Okay. So those are all the examples I'm going to give you for that particular set of examples. But I want to come back to this idea that I said before. You know, every relative extremum is a critical point. Okay, but not every critical point is a relative extremum. And let me show you a picture from your book that I think does a good job of showing this, right? So here you have a critical point, and it is a relative extremum, right? This is a stationary point, in fact, right? Here you have a critical point. It's not a stationary point. It's a cusp, and so it's a place where the function is not differentiable. Okay, and it also happens to be a relative maximum. So you've got a relative maximum, relative maximum. Similarly, here you've got a relative minimum and a relative minimum at these, in this case, a stationary point, and in this case, a place where the function is not differentiable. But you can have stationary points like this, right, where the derivative is 0, but nevertheless, that point is not a relative extremum, right? It's not a relative minimum or a maximum. And same way here. You can also have places where the function is not differentiable, like this, and nevertheless the function does not have a relative extremum at that point, right? So there are cases where you know, where you don't have relative extrema even where you have a critical point. Okay. So how do you tell, right? How can you tell if you have relative extrema? Well, here's one way to do it, right? So, and this is called the first derivative test. So suppose that f is continuous at a critical point x naught. So x naught is a critical point. It's not necessarily a relative extremum, but it is a critical point, right? So suppose that f is continuous at this critical point x naught. If f prime changes from positive to negative at x naught, so if it changes from, from positive to negative at x naught, then x naught is a relative maximum, right? So if x naught is a critical point and f prime changes sign at x naught, then x naught is a relative maximum. If x prime changes from negative to positive at x naught, then x naught is a relative minimum. And then if f prime does not change sign at x naught, then x naught is not a relative extremum. So this is one way to tell where you have relative extrema. Okay, so first of all, you find the critical points, and then you determine if the derivative is changing sign at that critical point. And you can do this the same way that we did in 4.1, making a sign chart and all of that stuff. But anyway, here's a picture to kind of, like if you're not quite capturing what I'm saying, like here's a picture that might help you, right? So here the derivative, so if you imagine that this is your function, right? Clearly you've got a relative maximum. Well, notice that your derivative up until this point is positive because the function's increasing, right? And then here the function's decreasing, and so your derivative is negative. So the point, this point right here, for one thing, it's a stationary point, so it's a critical point. And for another thing, the derivative is changing sign from positive to negative, and that means you've got a maximum, a relative maximum. And then you can go through a similar line of reasoning to convince yourself that you get a relative minimum when you have a critical point where the derivative of the function changes sign. Okay. All right, so let's look at this example. Find the relative extrema of this function here. We've already done some of the work, right? So let's find the relative extrema of f of x equals 3x to the 5/3 minus 15x to the 2/3. Okay, so based on the work that we did in example 1 part B, we already know that the critical points are 0 and 2. Okay, now to determine if those critical points are extrema, we need to determine if the function is, if the derivative is changing sign at those points. And the only way to do that is make a sign chart, right? Okay, so we have all the numbers to the left of 0. We'll say negative infinity to 0. And then we have the numbers between 0 and 2. And then we have the numbers bigger than 2, right? 2 to infinity. And then we're going to plug these into that first derivative to see where it's positive and where it's negative. Okay, so let's do that. Plugging something in here like -1, right? Here was my, where was my derivative actually? Right here. This is a good place to plug it in, right? So if I plug in -1 here, I'm going to get -1 minus 2 is negative. -1 to the 1/3, that's the cube root of -1, that's also negative. So I get a negative divided by a negative, that'll make a positive. Okay. What if I plug in something between 0 and 2, like 1? Well, I plug in 1 minus 2 is negative, so I get a negative in the numerator. 1 to the 1/3, that's the cube root of 1, that's positive. So I get a negative divided by a positive, and that's a negative. And then plugging in something bigger than 2, like 3. You get a positive here, positive there. It's a positive divided by a positive, and that makes a positive. Okay, so both of those critical points, 0 and 2, they're both relative extrema, and I can be even more precise about what kind of extrema they are, right? Because at 0, right at 0, I'm changing from, the derivative is changing from positive to negative, right? And so it must be a maximum, right? So I have a relative max at x equals 0. And in fact, if you wanted to give the point, right, that's just the x coordinate. If you wanted to give the full point and get the x and y coordinate, then you need to plug that in to the original function, not to the derivative, but to the original function, right? So f of 0, well, it happens to be 0 in this case, right? So you have a relative maximum at the point 0, 0. Okay, from here to here, the derivative is going from negative to positive, and so it must be a relative minimum. So you've got a relative minimum at x equals 2. The full point would be, 2 f of 2. And again, you would plug that in here to figure out how much that is. I think that's going to be pretty nasty, right? Gosh, 2 to the 5/3 power, I don't know, that's some nasty thing. Maybe I'll give an approximation instead of an exact answer. Let me see. 3 times 2 to the 5/3 minus 15 times 2 to the 2/3 is negative 9 times 2 to the 2/3, or approximately negative 14.3. Okay, I'm curious to look at this function in Desmos now. So just to satisfy my own curiosity. Whoops. That's not what I want. This is what I want. So let's do 3x to the 5/3 minus 15x to the 2/3. Ooh, what a crazy looking function. Now what did we say? We said that we would have a relative maximum at 0. Yeah, it looks like it, right? You've got that cusp there. And then we also said we'd have a relative minimum at 2. Let me change this step back to 1 or something. So minimum at 2, huh? At 2. Yep, looks like it. Okay, so that's interesting, right? Okay, very good. Okay. Now, so that's the first derivative test, right? That's the way the first derivative test, and secretly you've been doing the first derivative test all this time in 4.1, right? It's just that now we're calling these points where you change from increasing to decreasing, we're calling these points relative extrema, okay? Okay, so now the second derivative test. So this is another way to do the same thing, right? So note that if x0 is a stationary point and f is concave up, then x0 must be a relative minimum. Similarly, if f is concave down, then x0 is a relative maximum, right? You can see that in this picture here. So if you've got something that's concave up, and you know that this is a stationary point, well, then clearly this point must be a minimum, okay? And here, if you've got something that's concave down, and you know that this is a critical point or a stationary point, then clearly this must be a maximum. Holy schmoly. I need to stop recording videos today because I think my brain is getting a little tired. But yeah, so hopefully that makes some intuitive sense to you, and we call that the second derivative test, okay? So suppose that f is twice differentiable at x0. If f prime of x0 equals 0, so in other words x0 is a stationary point, and f double prime of x0 is greater than 0, so if f double prime at x0 is positive, then f has a relative minimum at x0. If f prime of x0 equals 0 and f double prime is negative, then f has a relative maximum, okay? Because here you're concave up, so you have a minimum. Here you're concave down, so you have a maximum. And then finally, if f double prime equals 0, then the test is inconclusive. So second derivative test is really nice, but I do need to point out that it does have some caveats, right? So the first caveat is this. This only works for stationary points. It doesn't work for points. It doesn't work for other critical points, right? In particular, it doesn't work for critical points that are places where the derivative ceases to exist, right? So that's one thing that the second derivative test doesn't handle. And then the other caveat is this part C right here, is that if the second derivative equals 0, then the test is actually inconclusive, and so then you have to go back and use the first derivative test instead. So the first derivative test will work regardless, okay? The second derivative test has a couple of caveats, but it is a nice tool. It makes things a little bit easier sometimes, and so let me give you an example of the second derivative test in action. Let's find the relative extrema of this function here. So f of x equals 3x to the fifth minus 5x cubed. Okay. So let's do this using the second derivative test. Okay. So first of all, we're going to take the first derivative. So that's going to be 15x to the fourth minus 15x squared, right? And then we're going to set that equal to 0 and solve for x. So if I set that equal to 0, well, first of all, I can factor out a 15x squared, and I'd be left with x squared minus 1. Okay, so we'd have 15x squared times x plus 1 times x minus 1 equals 0. There aren't any places where this function fails to exist, so the function is differentiable everywhere, which is nice because that means that was one of the caveats of the second derivative test, right? So we don't have to worry about that. But we get x equals 0 or 1 or negative 1. Okay? So these are all critical points, right? They're all critical points. But the question is, are they relative extrema? And so one way that you can figure out if they're relative extrema would be to now make a sign chart, right? Apply the first derivative test. But a second way, a different way to figure out if they're relative extrema is to now take the second derivative. That's going to be 60x cubed plus, or minus 30x, right? So you take that second derivative, and now you plug these values into the second derivative. Okay? So f double prime of 0 is 0. Ugh. So the test is inconclusive. That's okay. We'll make a sign chart for that one in a second. What about f double prime of 1? F double prime of 1. So if I plug in 1, I get 60 minus 30. That's 30. It's greater than 0. Okay? So remember, that means that you're concave up. So x equals 1 is a critical point, and the function is concave up there. That means that it must be a minimum. Right? So we'll say relative min at x equals 1. Okay, what about f double prime of negative 1? Negative 1 cubed is negative 1. Negative 1 times 60 is negative 60. Negative 1 times negative 30 is positive 30. That's going to give you negative 30, which is less than 0. Okay, so that tells you that you have, so that tells you you're concave down, and you've got a critical point there. So that critical point must be a relative maximum. So you've got a relative maximum at x equals negative 1. So now we have to figure out about this x equals 0 business. Since the test was inconclusive, we have to make a sign chart for that. So let's plug in a test point. And remember, when you're doing the sign chart thing, that's the first derivative test. So you're going to plug this into the first derivative, not the second one. But to the left of 0, I could choose something like negative 1. If I plug that into the first function, first derivative, negative 1 to the fourth is 1. Negative 1 squared is 1. This is just 15 minus 15. It's just 0. Well, that's not good. Oh, duh. It's because, okay, I'm sorry. I meant for this to be 1. No, I did mean for it to be 0. Oh, but I can't use 1 because 1 is already, okay, so scratch that. Let me try this again. Okay, the problem with what I was trying to do is that 1 is a critical point. You can't use your critical point as a test point. In fact, I already know that -1 and +1 are critical points, so I need to plug in, when I choose my test points, they need to be between 0 and 1. They need to be between -1 and +1, not including 0. Okay, so when I plug in something to the left of 0, it can't be 1. It needs to be like -0.5. But anyway, if I plug in -0.5, -0.5 to the fourth is something really small. -0.5 squared is +0.25, but this number is going to be bigger than that one. So when I subtract these, I'm going to get a negative value. Maybe it would have been easier here, right? If I plug it in here in the factored form, it's a little bit easier. So this is positive, this would be positive, and this would be negative. A positive times a negative is a negative, right? Okay, now if I plug in something, and maybe instead of calling it -1, I should have called it -1, right? Anyway, now if I plug in something between 0 and 1, like +1/2, +1/2 squared. Hold on. Okay, let me try this one more time. If I plug in -1/2, -1/2 squared is positive. -1/2 plus 1 is positive. -1/2 minus 1 is negative. Okay, positive times positive is negative. Okay, good. That checks out. Okay, now if I plug in +1/2, +1/2 squared is positive. +1/2 plus 1 is still positive. +1/2 minus 1 is still negative. So it's still negative there. Okay, well that's interesting, right? That tells me that so here I'm so here I'm decreasing, and here I'm still decreasing. If that's the case, I've got something that looks kind of like that, right? Which means I don't have a relative extrema, extremum, right? So I would say no relative extrema or extremum at x equals 0. Okay, so I've got a relative minimum at x equals 1, a relative maximum at x equals -1, and no relative extremum at x equals 0. Goodness gracious. I don't know why that was so difficult for me at first, but there you go. Okay, so that was number 3. Now, the last thing that I want to do in this section is talk a little bit about graphing polynomials, and then in the next section we'll talk more about graphing other kinds of functions, rational functions in particular. But let's just talk about graphing polynomials for now. So in order to do that, you may remember from your algebra / pre-calculus days that the way that you would typically graph a polynomial is you would find all of its zeros or all of its roots, depending on the vocabulary that you used in your pre-calculus class. And when you found the roots, it could be the case that you end up with multiple factors of the same, multiple of the same factors, right? And so let's say that you have a linear factor x minus r, and it's a factor of your original polynomial m times. Well, then we say that that factor is a factor of multiplicity m. We call m the multiplicity. Another way to say that is if x minus r to the m power divides this polynomial, but x minus r to the m plus 1 does not, then r is a root, or 0, of multiplicity m. Okay. Now, the reason this is important is because the parity of the multiplicity of your 0 tells you whether or not you're going to cross the x-axis or just touch the x-axis, right? So if m is odd, then the graph of the polynomial p crosses the x-axis at r. And if m is even, then the graph of p touches but does not cross the x-axis at r. Okay? So that's important to know. And just to practice with that concept, let's see if we can describe the x-intercepts of this function. So f of x equals x cubed times 3x minus 4 times x plus 2 squared. Okay, so let's see if we can describe the x-intercepts. Well, so first of all, you're going to have x-intercepts at 0, 4/3, and -2, right? If you imagine setting this function equal to 0 and then solving each part, right, you would say x cubed equals 0, or 3x minus 4 equals 0, or x plus 2 squared equals 0. And if you solve each of those individual parts, you're going to get x equals 0, x equals 4/3, x equals -2. So the x-intercepts are 0. Now, it's 0 multiplicity 3, right? 4/3 multiplicity 1. Okay, and then -2 multiplicity 2. So what does that tell us? So to describe this, then we would say here at 0 and 4/3, the graph is going to cross the x-axis, right? So f crosses the x-axis. Why? Because their multiplicities are odd. Okay, so f is going to cross the x-axis there. At x equals, or at -2, f is going to touch, but does not cross. The x-axis. Okay. Why? Because its multiplicity is even, right? Its multiplicity is even. So it touches, but it doesn't cross the x-axis. Okay. So with that out of the way now, let's graph some polynomial functions. And you may wonder to yourself, well, but why would we do this if this is something that, you know, is done in algebra / pre-calculus? Why are we bothering to do it in calculus? And the answer is because in pre-calculus you didn't have all the tools to properly graph a polynomial function, but now you do. I'll show you what I mean. Let's graph f of x equals x cubed minus 3x plus 2. So to begin with, we're going to want to find the zeros, right? So I'm just going to set f of x equal to 0, and then solve for x. Okay, so for this particular function, these are kind of hard for me. So I think what I'm going to do is I'm going to use the the rational roots theorem. I'm going to say the possible rational roots are going to be factors of 2 divided by factors of 1, right? So that's going to be 2 or 1, positive or negative. And then I'm going to test these. You can test these by just plugging them in directly or by using synthetic division. But if I plug in 1, for example, 1 was a possibility. If I plug in 1, I get 1 cubed, and then 3 times 1 is 3. 1 minus 3 is -2. -2 plus 2 is indeed 0. So I know that 1 is going to be a 0 of this, or a root of this polynomial equation. So setting up the synthetic division, I have 1x cubed plus 0x squared minus 3x plus 2. 1, 1, 1, 1, -2, -2, 0. If this doesn't look familiar to you, then I feel bad for you. If it doesn't look familiar to you, set up a Zoom meeting with me and I'll walk you through it. Okay? But anyway, so this, so now I can say, all right, so the factorization must be x minus 1 times x squared plus x minus 2. Okay? All right, this little piece I can factor now a little bit easier. I've got x minus 1, x plus 2, and x minus 1. Ooh, interesting, right? Okay, because I have an x minus 1 multiplicity 2 times x plus 2. Alright, so what does that tell us? That tells us that we have x-intercepts at 1 and at negative 2, but the x-intercept at 1 is a multiplicity 2, and so the graph will touch but not cross the x-axis at 1. Okay, so all of this was information that you had from pre-calculus, right? So you could do this problem. Up until this point, we haven't used any calculus at all. Let me just write down. So x int at 1, multiplicity 2, and negative 2, multiplicity 1. Okay, so that's the first step in the process. But that's not enough all by itself in order for us to be able to graph the function, okay? Because let me just, well, so we know that we have x-intercepts at 1 and at negative 2. Okay, so we know this. What we don't know is, oh, we could also say this. So you also knew this from pre-algebra, or pre-algebra, from pre-calculus. You knew this from pre-calculus. You could look at the end behavior of the function, right? So you could say, maybe you didn't express it in terms of limits, but we can express it in terms of limits now, right? Limit as x approaches positive infinity of this polynomial is just going to be positive infinity, right? Limit as x approaches negative infinity of this polynomial is going to be negative infinity. Okay, and so you know that from this point you're going to be going to negative infinity. As x goes to negative infinity, f of x goes to negative infinity, and from this point you're going to be going up to positive infinity. So we know it looks like that. And then in the middle we can figure out what's going on, because at 1 we have an even multiplicity, which means that right here at 1 it's not going to cross, it's just going to touch and then come back up. And then at negative 2 we have an odd multiplicity. That means that the function actually crosses through right there. And so this is the function that you end up with, right? The problem is we don't know where this maximum occurs. Right? We don't know where this maximum occurs. The only way to find that maximum is to use calculus techniques, right? So that's the real issue here, is that we don't know where the maximum occurs. So let's apply our calculus now to see if we can find the relative extrema of this original function. So to do that, I'm going to take the derivative, right? I'm going to say f prime of x equals 3x squared minus 3. I'm going to set the derivative equal to 0, and then I'm going to solve. Man, we've done this one a lot, haven't we? This is 3 times x plus 1 times x minus 1. We must have done this one already. But anyway, we get x equals negative 1, or x equals positive 1. And now, to decide if either or both of those are relative extrema, we can use second derivative test. Second derivative is going to be 6x. Okay, if I plug in negative 1, I get 6 times negative 1, that's negative 6, which is less than 0. If the second derivative is less than 0, that means you're concave down, so you must have a maximum at negative 1, right? So this implies that you have a relative max at x equals negative 1. Okay, what about f double prime of 1? That's 6 times 1, which is 6, which is positive. That means you're concave up, which means that you must have a relative minimum at x equals positive 1. Okay, so let's see if we can put those pieces onto our graph now, right? So we know that we have a relative minimum at x equals 1. Well, that's not surprising to us. We knew that because the graph was going to touch but not cross the x-axis there, so we knew we had to have a relative minimum. But we also know that we have a relative maximum at negative 1, so we can draw a slightly better picture. In fact, another thing we could do is we could find, okay, so it's a relative maximum at -1. What's the y coordinate, right? So your relative maximum is going to be the point -1, f of -1. That's -1, and then f of -1 is going to be -1 plus 3 is 2, plus 2 is 4. So you've got a relative maximum at -1, 4. We could also find the y-intercept. Okay? If we plug in 0 here, we're going to get a y-intercept of 2. So the y-intercept is the point 0, 2. Okay, so putting all of this information on there. So we've got x-intercept there and there, y-intercept there, and all of that stuff you knew from pre-calculus, but now what you know from calculus that you didn't know from pre-calculus is that you've also got -1, 4. That's your relative maximum. Okay? And so now you get a much better picture of what the function actually looks like. See, so that's much better than this. Okay? So that's all I have to say for this section. I've probably been talking for a while. How long have I been talking? Oh, 46 minutes. So we could look at this in Desmos. I'll let you do that on your own time if you want to compare the graph that we just came up with what you would come up with in Desmos. But now you have all of the tools that you need in order to properly graph a polynomial function. I guess another thing that I could say just quickly is that second derivative also tells you where you're concave up and concave down, right? So you're concave up whenever this second derivative is positive, you're concave down whenever this second derivative is negative, and the only place it could change is when x equals 0, okay? If x is less than 0, then second derivative is negative, right? If x is greater than 0, then second derivative is positive. So you're going to be concave down if you're less than 0 and concave up if you're greater than 0. And notice that that's exactly what our picture shows us, right? If x is less than 0, concave down. If x is greater than 0, concave up. Okay. Anyway, so that's that. We'll do some more of this graphing in the next section as well.